Yeah, so it's live now.
Okay. So maybe we can get started. So apologies to those of you watching online. We've had difficulties keeping up commitment and participation in class. So we have fewer and fewer students to help out to present. So we hope you'll be able to also help participate in the lecture because some of our student lecturers have held out at the last minute. So today's topic is really interesting. Actually, I quite like the subject of inverse reinforcement learning. And so Juget, Sarah, and Bala will be responsible for parts of the lecture, and the rest of it we'll try to cover together as a collective. So Jen and Y, you are online. I hope you will join us in helping to go through the contents of the lecture. So let's start with you first. Tell us what IRL is. That's mean in real life.
Okay, good afternoon, everyone. Today's topic is inverse reinforcement learning. I will cover the part 1, first portion. The rest of the portion will be covered by Sarah and Bala. I will go through the importance, the needs to use inverse reinforcement learning, what are the challenges, and a comparison between reinforcement learning and the inverse reinforcement learning. And how do we overcome the challenges by using features matching and maximum margin. Why do we need IRL? For example, if we want to learn to drive from point A to point B, the destination, in a shorter time, what other options do we have? There can be 2 options. Option 1, someone can tell us where's the destination for us to reach. And then the driver, which is the learner, will try to derive the driving actions from the instruction given. That is option 1. For option 2, we can have an expert to demonstrate the driving actions. And from there, we will reach an outcome or conclusion. That is the destination to reach. So in a way, option 2 would be better. Why is that so? Because it is easier to demonstrate how to reach a destination in a faster and safer way, rather than to specify the reward function in more detail, as there are many path and traffic conditions to consider in the description of the reward function. So far, okay. So where does the reward function? There are many types of reward functions. In computer games, the reward is the score of a game. But in real-world scenarios, that could be different because the scenarios always change. For example, for robotics, it can be a robot trying to pour water into a jug, and dialogue for agents to interact with people, and autonomous driving try to reach a destination in a safe and faster way. Because of the scenarios are not fixed, so it is easier to provide expert data for the agent to figure out what could be the possible reward. And that is inverse reinforcement learning. Why should we learn the reward? We can always copy the expert behavior and then get the expected reward. But that is not good enough because the behavior provided might not capture the salient parts of the behavior, and we do not know whether the expert has different capabilities. So the award that the reward that we learn might not be good enough. It is better to know what is the reason behind that the expert is trying to achieve, and to better learn and restructure the reward, perform the goal using its capability, which is greater than the capability of the expert. So that is the goal that we want to achieve, to learn and make the reward better. However, under the inverse reinforcement learning, there are few challenges. The first one, an underdefined problem is difficult. In this case, because of the lack of context, we do not know why the expert behaved in that way. So it's difficult to define the problem. And it is difficult to evaluate a learned reward. This is due to there isn't any guidelines for evaluation. So we are unable to confirm whether the learned reward is a correct one. Without knowing the scenarios, we might not be able to confirm whether that is the destination or just a stop due to some incident along the way. And the third one, demonstrations may not be precisely optimal. In this case, the instruction given might not be from the real expert. And it could be due to the traffic condition and different features during the action was given. So there are quite a number of uncertainties. Any questions so far?
Any questions? Think it's okay?
Okay. Can I proceed?
Yeah, well, it's your lecture. You can proceed when you want.
Okay, the next one is to compare between reinforcement learning and inverse reinforcement learning. So for RL, the main input is the reward function. And what we want to get from it is the optimal policy. As for IRL, the input is the policy itself, which we want to get the reward function out of it, and based on the reward parameters. And with that, we will be able to further optimize the policy using the RL. However, what if all the policies we input are optimal? It may result in zero function. So we might want to specify the reward using the inner product of psi, which is the weight, and the feature vector. Just to add that psi is actually the weight that we can assign so that it can show how much we can trade off the different features. And example of the features are the number of lanes, traffic condition, and how to be away from the curb during the driving instructions or journey to the destination. Feature matching. This is to overcome the ambiguity that I mentioned just now. So so what we need to do is pick the right side and then to match the feature expectation under pi r side to the feature expectation of under pi star, which is the optimum policy. However, this is still ambiguous. The next method that we can consider is maximum margin. It is used to allow each demonstration to have a set of features map different from other demonstration. And what we want to have is to have the reward of the expert policy to be larger than the reward of other policies by the largest margin. But there are still issues with this maximum margin. One of them is maximizing the margin is a bit arbitrary. Because the policy with larger margin against other policies does not mean that it is better fit to the expert actual goal. However, it may remove some problem, but it's not good enough. The second issue that we have, no clear model of expert suboptimality, because expert might still have some possibility of making mistakes. And there is also constraint in the optimizing the problem, partly due to the linear function that the problem may actually be very tractable. With that, I will pass to Praveen.
Okay.
Yeah.
So we've had a lecture about, as I said, that's the last minute, so I'm going to try to take over that part. I'm not going to use the slides because 2 minutes ago I found a blog post that I think will help. So I apologize that I had to switch up a little bit. I'm going to try to put it on Slack and then try to go over that part. Second here as I work through this. So obviously cannot post. Okay, let's see. Minute here. Okay, so come back to the slides later. I'm going to switch over to my slides. Share screen. Great. So I'm going to try to go through some things together with you. So I'm going to try to post this. Somebody can try to copy this part to the blog post to Slack so that we can go through it. Okay, so I'll just try to step you through what I could see in the last couple of minutes on this. Let's see, maybe I can get rid of this part. Okay. Is that better? Okay, so we're looking through the reinforcement, inverse reinforcement problem. And so Ju already kindly told us a little bit about what the difference is between IRL and RLR, right? So in IRL, the problem is that what we want to do is find the reward function given sample trajectories and histories, right? So we're given that, and then we have to find the reward function actually being optimized, right? So it's inverse because we're not given. We're trying to learn the reward function rather than it being given in the reinforcement learning procedure, right? And we're trying to we're actually given the policy or versions of the policy that we could learn from the sample trajectory, right? So I think most of the lecture actually talks about this, but we have to proceed at the beginning, assuming that we have a policy pi that we're given, right? And so as Sergey also mentioned, this actually has a long history. It's called the inverse optimal control problems because optimal control has been around for many years in operations research as a problem to worry about, right? So this is again a very important thing when we can observe behavior, and we'd like to know what the reason why somebody is doing that behavior, right? So I think Sergey saw a video where there's an adult trying to put books in the bookcase, but because the bookcase door is closed, he can't put them in, and there's a toddler in the room observing this, and then actually ends up opening the door for the person to put the books in. So obviously the toddler's mental model is that, okay, I can see this person's not achieving their goal, but I have an idea of what his goal is, so I'm going to proactively open the door. So we can think about this. But there's a problem here is that in many cases the reward function is hard to know because it's ambiguous. I think there are lots of cases of that, even in the slides that there's this part here that Ju covered a bit to say that if you see a circle like this moving over to this, it's not clear exactly what the goal is, right? If you see that window, maybe the goal is to try to move it onto any triangle. Maybe it was to purposefully move it to the purple triangle. Maybe you're trying to move it right. So from a particular part of a trajectory, you may not know what the goal is. So there's an ambiguity there that we're not sure about. So all we can say is that given the observations, we will have to assume that there's some optimal type of behavior being encoded. So without the context, we can't know. So it's in some sense unlearnable, just like the normal supervised problem is. You cannot really say what your goal is, because when out of sample, you never know, right? So it's an ambiguity problem, but we're going to sort of not worry about that at all. We're just going to assume that the policy or that the sample trajectories being given are indications of optimal behavior, right? We're going to make that assumption. Right, so we can think of the idea of relearning. The reward function is actually a succinct description of the task because we are just saying which states of the environment are desirable, which states are not. Right, and as said here, the reward function is in many cases more robust, like Ju said, than the behavioral cloning because you can generalize that to unexpected environmental conditions. Just like the example with the toddler, if the door was open, you'd be able to put the books in, but because the door was closed, then the toddler can generalize and say, oh, the door needs to be open, and then the person can put the books in. Okay. So yeah, I think we can read this a little bit. In the case, it's perhaps very difficult to manually specify a reward function, right? So games, of course, we have a reward function that's very easy to understand. There's a score involved, right? But for many real-world tasks, that's very difficult. So as Ju pointed out, what does it mean to drive a car well, right? So can you write down a reward function for that? Okay. So let's go on to what was discussed in the lecture. So there were two parts of this. I think the first one we're going to go over a little bit, which is the max margin application. So we can first describe an MVP, right? Saying we have S as a set of states, A as the set of actions, R as a reward function that we're going to learn, and T is the transition probability matrix that's going to help us understand how we go about, and gamma here, which is the discount factor for future rewards, so that we can focus on the short term more importantly, right? So we're already going to start with some definitions that are from the Bellman equations that we studied previously. So we have the value function of a given policy, given the current state is, again, as we've seen many times, right? The reward at the current state plus a time factor discounted information between the transition probabilities given a previous state and the policy for that state, right? Times the actual value in the next state, right? So this is just time discounted so that we can say we prefer current rewards to future rewards, right? And then we also have the standard Q function. The Q function is, of course, action specific. So it says for a specific action, we're going to look at the reward and then just have the dependence on the action as well. So everyone's, I think, pretty familiar with that, right? So we're going to look at some of the blog posts in this thing with respect to the free algorithms that have been proposed that Ju also mentioned. Okay, so there's three different things that are going on. The first one is when you have a tabular representation, right? So there's a small state space, so we can actually write out all of the marginals. We have an optimal policy, which is already known, and we're now trying to reverse engineer the reward function. And then we'll get to more complicated places where, for example, we're going to remove the restriction on the small state space, okay, and then say, okay, actually, we don't know the policy. This is where we're trying to head, right? So we just have examples, trajectories of what's going on, and we're going to sample them from our policy by running some simulation, right? So we're going to get sample trajectories, going to try to relearn the reward function from there, and then go on the other way. So later on, when Bala gets to the final part, we'll see how we can connect it with generative adversarial networks, because we can link these two parts together, right? The inference of the reward function and then the generation of the policy later on. Okay, so this is where I'm going to start to need help, because that's all the easy stuff, right? That's the motivation. So the math is a little bit harder. Like I said, I watched the lecture in the car, so I can't actually watch the math, otherwise I'd crash. So I also want to be a good driver, right? I don't want to do it in a simulator only. I have to actually drive on the road. So so we'll look at this one, right? So we're going to look at a finite state space. So we have to say that what we have each state some set of actions not picked by the policy. So we actually have a policy that picks a particular action, and of course we don't pick the other k-1 actions. So the whole point of this is, okay, well, if it didn't pick that action, it must be worse than the other ones. You can think of it from an advantage function point of view, right? There's one thing that the policy decided, so that must be the optimum one. So we can think of it in an optimality variable type of sense that we talked about last week in the variational learning part, right? Which is why he said you need that part to understand this lecture, right? So you're going to assume you have optimality variables that when the policy generates an action, it must be optimal, right? So what we want to do is really simple, right? If you remember your SVM machine learning stuff, it's basically going to maximize the margin, right? So what does that mean? It means we want to discriminate between the action that was actually taken by the policy, right, that's prescribed by the policy, and all the other actions. We're going to try to push them as far away from the decision boundary on what the actual margin is. And it's called a maximum entropy approach because, in fact, we want to have the most uncertainty in the actual policy itself, in the sense that we don't want to overly constrain any other things besides what the policy actually does, right? So there can be many other ways. There are probably an infinite number of policies that can follow the optimal policy, but we want to choose the policy that's the least constrained on it, right? So we want to leave all of the other constraints that could possibly be engineered out of the equation. Say this succinctly describes why this particular action was taken, right? So that's the idea of maximum margin, right? So okay, so let's try to look at this, right? I'll need some help with this. We can order these actions, other actions arbitrarily for each state and construct k-1 non-policy transition matrices. Right? Ti is the n by n transition matrix containing state transition probabilities for always treating the IF non-policy action in each respective state. So here, Ti is an action that's not the one that the policy took, right? Everyone agree with that? Okay. So what we want to do is then define a solution set as follows, right? So can we decompose what this means? Anyone want to take a try at this? So the solution sets can be specified as for all transitions and each time step. I think that is right. Is that right? For each time step. So the I is the subscript, so I guess it's a time step. Can you see that? Maybe we can blow it up a little bit. Scroll down a little bit. A little bigger now. Yeah. So we have here Ti is from the set of all t i's not in the policy, transition of the policy minus the transition of the any action that wasn't in the policy times the identity matrix of the times the discounted information for the transitions on the policy over that. So I guess they're going to explain it, right? So let's read the bottom part. So the solution set is the set of all reward functions for which the given policy is optimal. This means that the policy chosen action by S at any state corresponds to an expected value which is larger or equal to the expected value of all other actions in this state, right? So this is summarizing that, right? So which is equivalent to for all states, for all actions, this inequality must hold true, that the actual transition for the actual transition taken by the policy, is that correct? Is going to be bigger than the rewards for cases where, what's this? You force the expected value of the policy actions, this part here, right? Okay, to be larger or equal to the expected values of any other action for all states. Did we parse that properly?
First part is the first part, I guess, is the YFS, which is the action given by the policy. And the second part is the rest of all the other things.
These are all the other possible actions.
All the possible actions that it was not included in the. So we want to push the left side as much as possible, and the rest of all other things as well as.
Mm-hmm. So A here, is it? These are all of the possible actions, or all of the possible actions minus the one that the policy is making?
That one is for all the actions.
All the actions.
Before that, and then the first expectation is the left-hand side.
Mm-hmm.
Is you see the YFS, that means that on the policy that decides a particular action.
This one
can
here.
be one action, for
Mm-hmm.
example.
Okay.
And then on the other side is the rest of the other actions that may not be in the trajectory. For example, on that state, an action was picked up by best trajectory, and that is the action that we consider on the left-hand side. And the rest of other actions that we might have taken, that we want to push them down. So definitely this action must be higher, that's why it's on the left-hand side. The action that we do must be higher, so we want.
Okay. Any questions? So I'm not clear whether A here also includes the optimal action.
I think it's because most of the equations that I saw, whenever they didn't explicitly mention a particular action, that means the set of all the actions. Maybe.
Set of all the actions. Yeah, I think it's also for all of the actions,
Yeah,
right? I think let's go back up to the top and see what yeah. So this is all actions, not including the optimal action, right? Okay, but as Wee-sun said, well, it's sort of it's just one out of many, so it doesn't matter. We're just specifying greater or equal then, right? Is that how we're expressing it? Okay, so we can reformulate this as using matrices and vectors for transitions, where V, the optimal policy is an n-dimensional vector containing the state values under the policy. Right, so we can write this in this form. So we just have two vectors, right? And we're just multiplying these. The transition matrix times the vector, which is going to give us our reward, and again for any other transition, right? Well, this is saying the same thing in vector matrix format, right? So let R be an n-dimensional vector containing the rewards for all of the n states in S, all of our states, right? So we're saying we are going through these particular n states as the optimal thing that our optimal policy would choose, right? Then we can rewrite the policy's value as something like this. The value of the policy, so now we're introduced, just factoring it out, is just, again, the Bellman equation written in matrix form, right? Okay, because we have our discount variable, our transition matrix, and the values of the states. And then we can define it back down to here through the algebraic manipulation, right? Okay. So I don't know where to go from here. Right. To get more intuition for the definition, can you guys read that? I don't know. I can see it very clearly on my monitor, but I don't see it very well there. Too much. Done. To get more intuition for the definition that of the solution set, note that the transition sequence of the optimal policy minus the transition sequence of an arbitrary policy tells us how much the transition probability is changed by using the optimal policy instead of some other set of actions, right? So that's what this term stands for over here, right? You see it over here as well, okay? We multiply this by this identity minus the discounted information, which is equal to the vectorized value function. Thus, the product tells us for each state, for each time step in the transition, how much the expected value was changed by using the policy instead of some other action. So we're doing it at each discrete time step. We're saying for that time step, what was the cost, right? Can I say that? The cost involved for taking that step as opposed to some other unoptimal time action, right? And I'm aggregating all of these together through this matrix operation, right? So each one of these is a particular state. I'm thinking of, let's say at step 500, I have a choice between this action and k minus one other actions. So I want to quantify the cost of taking that an unoptimized action compared to the optimized one, right? So what this ends up with is that we want these information, this product values for each one of these states to be positive, right? We want the optimal value to represent something that, like the advantage function, a positive reason why we would choose that action over an average or unoptimal action. They all have to be positive, right? So that's why we have this inequality to be positive, okay? So this inequality gives us a set of linear inequalities, right? One for each state in the trajectory, for each of the k minus one non-policy actions. I have to choose between all of the A actions, script A actions at each time step, right? And so I can set up a linear programming algorithm for that. Okay. So let's see. Let's look at a very simple example that will help us understand how this would be applied in practice. Let's look at 3 states and 2 actions with the reward structure as shown. Okay. I haven't seen this before, so hopefully it actually is accurate. Let's hope so. We have 3 states, S0, S1, and S2, and 2 actions, blue or orange, right? With a transition of S1 to from S0 and blue. So S1 be 40%, or going to S2 with 60%. Okay, so let's hope we can go through this diagram. So let's say we have an optimal policy, at each state, we know exactly what we're going to do. We're going to choose one of the two actions, blue or orange, right? So then I have this matrix probability that I'm going to get. Where does this? Oh, this is our transition matrix, right? Yeah. Okay. So that looks correct. Okay. So our policy is going to be encoded into the matrix, right? It tells us exactly what we're going to do at each time step. So then we can construct the inequalities from these two pieces of information. Okay, so they'll look a little bit like that. So again, we have the Bellman equation. Well, not here. We can construct that. Okay. I don't know whether this helps a lot. Did you follow the example? Anyone want to go through or detail it?
I think it's the same as in the previous case.
Okay.
At the last equation, we got for the policy that we have, first line, I believe.
This one.
Yeah, that line. And so there's a bunch of reward for each state. There is a reward component, and that's a reward vector, right?
Yes, this is the reward vector.
This is kind of the advantage quantity, some sort of quantity that is associated for choosing that action in that particular state. So on the left hand side is a bunch of state 1, state 2, state 3. And the column is actually a bunch of actions.
Actions.
It's good. There's two actions here.
There's only two actions, right? Blue or orange.
Okay. And this is a probability. This is a transition probability. Yeah, this transition probability from state n to state n, state 1 to n to state 1 to n. It's corresponding to.
Right, so it says here, these inequalities contain 3 unknown rewards for each state, right? The estimated reward for being in state S0, S1, and S2, which we want to estimate, right? So it looks most rewarding to be sitting in state S1 for this. Can I say that? This simplifies the free-falling equations. Of course, the top one is useful. So let's see if our vectorized original reward function of reward, where we place the most reward in this first state as opposed to 0 or 2, provides this inequality, and it does, right? It's higher. Obviously, this is only positive term, so that this one is the only one that's going to help with that. Okay. So as we can see, the original reward function is part of our solution set, right? However, it's quite obvious that the solution set will contain many more reward functions. Many of them are degenerate. For example, assigning a function which assigns 0 to all states will also always be a solution. Okay, so that's a problem. How can we know which of the many reward functions in our solution set is the correct one? In the next section, we will look at some heuristics to get rid of those. Right. So it says here, also note that this can go both ways. For a given policy, there are many reward functions. For a given reward function, there might be more than one possible policy. Right. So there's ambiguity in both directions. Okay. So in the paper by Ng and Russell, they came up with some heuristics to do this. I don't remember. I don't think Sergey covered this paper in depth in the lecture, right? Yeah. So let's see, pick the reward function from our solution set, which makes the difference between as large as possible. So this is again like max margin, right? Just try to separate things out as much as possible. This will successfully remove many of the degenerate reward functions, but it also makes a very strong assumption on the expert's behavior, right? So we don't want that. Sometimes we have this problem where an optimal policy just picks up on some extreme cases, right? So the second heuristic proposed is that many small rewards are more natural and should be preferred. So this is in countering this part, right? You're saying, I want the one that's optimizing the reward, but maybe I don't want it to be dependent on any one component. So for example, I guess, again, I'm making this up, but maybe you guys can help me with this. If I have a trajectory that consists of many time steps, and I find a policy that gets one part of the trajectory with choosing the correct action very well, and it creates a huge amount of reward, I may still not prefer that over one that makes incremental correct changes that matches the policy better over many time steps, right? So that might be a case where it's more natural, right? So an example is like, let's say I'm driving a car from destination A and B. Okay, so if I have a trajectory that follows all of the states pretty well, and I end up at my destination, that might be preferred than say if I go off the road a little bit, take a shortcut by jumping through the air and then landing in state B, some type of shortcut in the game, for example. Maybe that would be a drastic change of the way that I get to a good reward function, but it's too far off from the policy, so I would not prefer to do that. Can I say that? Okay. So that's why they say let's minimize for the L1 norm. So that's just similar to what we were saying. This isn't really weight decay. Weight decay is L2, but never mind. So I would think this is more L2, but I haven't read the paper, so they proposed the L1 for this. So this is looking at, I think this is related to the part where they talk about feature expectation matching. Because when you talk about feature expectation, you're talking about each individual feature, which would be a difference on the L1 component rather than the L2 component. Okay. So in addition, an upper bound for the values of the reward function are enforced. I'm not clear why you would do this. So it says there's a maximum reward. The estimated reward cannot exceed that. I'm not sure when this would happen. Why would you be able to get a bigger reward than the actual reward? Maybe it's because, no, I can't figure that out. In addition, an upper
solution.
Huh?
It's a solution of the equation.
I think this is a heuristic that they introduced in this paper, if I understand this correctly, right? Some heuristics to remove degenerate solutions. So it's supposed to help to remove degenerate solutions, so you can pick out a single best policy. Single best reward function.
Complex is just something you decide. It's not a value. It's probably known information.
Okay.
Yeah, that's what I was reading. Because you're saying that you enforce it instead of it being derived like heuristically.
Okay, so it's given to you that you have Rmax and you're just passing it along, that you cannot have a reward that's greater than that.
It sounds like it. It sounds like, say, I don't know, maybe chess is not a good example, but your maximum reward is whatever reward you have for winning the game, I guess.
Mm-hmm. So it's an upper bound.
I guess it also helps because otherwise you might have solutions that you can remove many solutions that converges to infinity or diverges to infinity.
Okay.
I'm guessing that's what they're trying to say.
Okay. Anyone else have insight, either here in the room or online?
You get I think they can't see get the PDF link for this because it's been blocked by the.
Oh, has it? It's actually not a PDF. It's a blog post. So let me try to put this online. So let me go to Slack and then dump it on the online or on general. This is the tutorial. Oh, it's just down here. Yeah, it's okay. Never mind. Leave it there. Does that help? Are you able to find it?
Yep.
Yeah. So we're now at about maybe 60% down the page. So we're looking at the infinite state space approach, right? So now, Sergey did hint that, in a small environment, this is actually quite tractable because you have marginals that are finite. But what happens if you have an infinite state space, right? So how do you do it? When you have a continuous states, right? So your S has real numbers in it, right? So now we have to deal with that.
Okay, I changed my mind. Now that I can see the whole thing, I think that actually the
This part
upper
here.
bound for them, they enforce the upper bound to go with the idea that if you go further up, there's one that says the second heuristic proposed by Ng and Russell in the same paper assumes that reward functions with many small rewards are more natural entry preferred.
Right.
So I guess this is a way for them to filter out the big rewards that they do not prefer because they feel that the heuristic is basically on this heuristic. So it's not like, say, there's a mathematical theorem or something, but it's more like I think they just want to enforce it to go with this heuristic.
Yeah, I took the second heuristic to mean exactly this, that they're putting this L1 norm on the approximate, estimated reward with the, this is another hyperparameter, right, that they're using. But you're saying that you think that both of these, the Rmax is still part of this part where you're trying to cap the reward function estimate from being too wild.
That seems to be my interpretation that's my interpretation from the beginning.
Okay. Certainly we can go into it a little bit more. If we want, we can dive into the paper. But I think maybe we continue with the next one first. And if we have time, we can go back to that. Okay. All right. So, right, if we want to use with infinite state space, we're going to have to use some other way of doing it. Because, there's an infinite number of possibilities for actions. So what we're going to use is function approximation, and then try to limit the algorithm to find a linear combination of the fixed, known, and bounded basis functions. Right. So now it's if you have a inventory of basis functions, then all you need to do is find some linear combination of those basis functions, right? That allows us to do linear programming. Right. Of course, when you do that, you're accepting some limitation that you can actually represent the correct reward function with that, right? Because you're now limited in the space of things that you can represent to some linear combination of the basis functions. So your basis functions have to be fairly, I guess, robust for that. Okay, so that's okay. Value approximation for each basis function. By the linearity of expectations, the value of the full estimated reward function will then be something like this. Right, it's just a linear combination. Right, okay. So how do they do this? Because the state space is too large, we can't do everything. So what we're going to do is estimate it using a sample subset of spaces, right? So we have a policy. Instead of using the policy directly, we're going to sample a subset of spaces, and then given those samples, again, use the first paper's idea, right? Just to separate out the actions that are optimal, assumed optimal from the optimal policy, and those which we could take as suboptimal actions and then use them. Right, so again, we can use a very similar method. Okay, let's see. Okay, So I don't think there's that much more to say here, right? This is just, do we want to try to cover this? Anyone want to weigh in? Real function might not be representable. We already know that. To resolve this issue, we have to relax our linear constraint and simply penalize when they're violated. So this is very similar in the support vector case. So if you remember your support vector machine literature, right, the basic version is a hard SVM, which says that there must be a satisfied solution, right? And in soft SVM, we say, well, you know, we'd like these things to be constraints, but we can't guarantee that they're not violated. So I add slack variables into them, right? So we're basically doing that. We're saying that we allow some penalty, right? How much the constraints are violated based on some hyperparameter, which is very similar to the hyperparameter that you see in SVM, right? So it doesn't say how to definitely optimize it, but basically you're now using a linear programming formulation. Maybe it's slightly easier than the quadratic programming formulation, which is a QP problem, which is in the SVM, but subject to the same types of inequality constraints, like the KKT conditions that we have in support vector. Okay, so what we can see here is the formulation above tries to maximize the smallest difference it can find, selects the best non-policy action, right, that's closest to the border between the optimal policy and not, and tries to maximize the difference to the policy in each state. So instead of, in the earlier case where we're saying all of the policies, we're trying to say all the policies that are, sorry, all the actions must be less than the best one, right? We're saying that the single best suboptimal policy must be maximally distinguished from the optimal policy, right? Do we get the difference there? So let me try to say it again. Let's say I have 5 actions, okay? And I have an optimal action that gets, reward 10. Okay, and 4 suboptimal actions that get reward less than that, right? So in the discrete space case, which we did at the beginning, right, where we said we're going to look at all of these things here, right? I think this one, right? It says that I'm going to optimize for all of the 4 possible suboptimal actions, right? I all want them to be less than this. Right? So instead, in this continuous state space one, we're saying, I don't care about all of them. Just like in SVM, I don't care about all the data points. I just care about the data point or the action that is closest to being optimal, but is not optimal. Right? So if I in that example, I have the optimal reward be 10 from a certain action, and I have suboptimal ones that are 8, 6, 4, and 2. I only care that the 8, right? That's the only thing that I care about. And I want to push whatever reward function in such a way that the 8 is pushed far away from the 10, so I can discriminate well between those 2 parts. That's what my reading of this is. Okay, so that was this part right here, right? You can see that the formulation above tries to maximize the smallest difference it could find. That is, it selects the best non-policy action, right? This is the suboptimal action, like reward of 8, and tries to maximize the difference between the policy action, in my example, a reward of 10, for each particular state. This is essentially the costly single-step deviation heuristic that we saw in the last section, just adapted for the case of large and infinite spaces, right? Okay. So I think that's a good point to get to the last part, which is when we have sample trajectories, right? So now we don't have any generator. We don't have a policy to generate our trajectory. This is just given some observations of behaviors by an agent, right? We don't have a way of creating them. So now we want to go ahead and actually do something about that. Learn the reward function from sampled points. And of course, we have to assume something about those samples, right? In particular, I think as was said in the lecture here, is that we actually have to assume that they're actually optimal behaviors, like the reward function is actually, the optimality variables for the policy are actually correct, right? Okay, so we want to estimate the soft optimal policy under the current reward and iterate accordingly on that. Okay. So again, we're going to use a linear combination of known, fixed, and bounded basis functions to approximate the true reward function and calculate the corresponding value for each basis function. So it's going to be an iterative process, right? We're going to start with some arbitrary policy. Let's call it pi1. This is going to lead to the GAN formulation later, right? So we generate some arbitrary policy. We use it to generate some random policy, right? And we're going to check whether that actual trajectory that was generated looks anything like the demonstrations or the trajectories that were in actual case, right? And so we want the expert trajectory to obtain more value than our generated one, right? And we can use that gradient then to help us move the random policy from pi1 to pi2, which is going to be more like the expert behavior. Idea is we're going to generate the policy such that it can match the actual trajectories, right? Okay, so it says optimally we want to compare many more trajectories, especially trajectories that are more competitive than random policies. I'm going to try to do this. After each new estimation of the reward function, we run a standard reinforcement learning algorithm to find a policy which is optimal for the current reward estimate. Right, so we already know how to do RL, so we just do RL on the reward function that's generated, right? That is going to generate the trajectory that we have. So we're going to say, given that our current reward function is like that, we're going to generate an optimal policy for it, and then we're going to compare the trajectories that is created with this optimum policy against the sampled actual trajectories that were demonstrated. Right? So it says that exactly here, right? So I'm going to generate a new policy, pi I, for that time step in which I have taken the current reward function that I've estimated and say, okay, if that was actually your reward function, you would be doing this, right? So I run that out, I roll that out, I get some trajectories, and then I say, well, you know, do those trajectories actually look like the ones that I got from the expert, right? And when there's no difference, then we've done our job perfectly. If there's a difference, then there's a gradient, and then I can optimize in such a way that I can get a better estimate of my reward, right? So after m iterations of the algorithm, the linear programming constraints will grow to something like that, right? And it says here, this algorithm runs for some large number of iterations until a satisfactory reward estimate is found, right? So yeah, it says we have to make two important assumptions. All right, we can generate, that means we have a generator, that's standard, right? And that given any reward function, we can generate a policy which is optimal for this reward function. This just says we know how to do RL, right? Okay. As an approach before, we might run into cases where the true reward function cannot be expressed. That's you know, the model representation problem, right? And we can penalize that, again, using the same types of constraints that were in the first part of the paper. Okay. So that's all that we're going to go through from this one. There's another paper that I found. I'll put this one online too. I was thinking of going through that, but again, it's a little hard to go through everything here. Sorry, I'm not supposed to show you that. So this is another IRL survey that you might, some of you might have found if you look through this. Did any of you see this? You were lecturing? Okay, so it took a couple minutes of Googling, but we can try to go through this if you'd like. Do we go through it, or do we want to cover the rest of the lecture? Okay, so did I put that on Slack already? Yeah, okay. So I think we've already talked about some of these, right? We talked about the basis function. Yeah, I think this looks like we already covered this, right? So we have to specify for all of the actions the probability of the current optimal policy. Estimate of the optimal policy has to be bigger than the one for a non-optimal policy, right? For all of the constraints. I don't know where the alphas went. The alphas, they're not even in this equation. Okay, okay, well, they're down here, right? So we basically have an alpha for each of the basis functions that is going to form our policy, right? Our sorry, not our policy, our value function. Huh?
Which might be the policy.
Yeah, it influences the policy, right? So we have the optimal one comes from the expert, which through demonstrations, for example, and then we have to compute these from a simulator that we can use to generate other policies, right? And so we're just going to accept that we have this bias problem that we can't necessarily represent everything that we'd like. To make it tractable, we'll just say it's linear, and then it becomes a linear programming problem. Yeah. Yes.
It's interesting to see V1 how the V1 to VG is actually different versions of the current policy.
Different versions of the current policy.
And we are weighting different versions. Because there's a linear combination of all these versions of these policies. And there is one version that should be, or maybe there is an expert's version as well, which is the best one. We know that. That's from the demonstration. Is it correct?
So you're saying all of these are policies in themselves?
Because we started with V1 initially, like it's totally random, and then we are slowly moving towards the expert's policy.
We're starting with, are we starting with V1? I thought we were starting with some, oh, I
Some
don't
policy
remember.
V1, let's say.
Policy or value function, which one? Because I think in the final section of the previous blog post which we looked at, we were looking at some pi 1, right? So that means I have a particular policy, a random policy that's generated, right?
And then we are iterating, just improving the policy over time.
Right.
Match the expert's policy.
Right.
If we successfully match it, we are indirectly knowing its reward function.
Right.
And then so we can extract the reward function and
right.
And so in this case, the linear programming aspect of this, this alpha 1 to alpha d is just different, some combinations, right? Some
yeah, it's a linear combination of VD, right? All the VDs, but I'm not so sure they generate a policy. They're basis functions, but on what basis are they?
All of them are same pi, which means.
Right, yeah. So they're specific to this particular policy, but they're functions of the value function, right? They're VD, right? V1 through VD. So their basis They're basis functions for calculating a value function, right?
On top, right? Over there, there's a pi I.
On top here, yes, this one.
The pi I.
Mm-hmm.
So in specific one, there is no I here. Alpha 1 to alpha D.
What, this one? There's no I, right?
Yeah.
Uh-huh.
It is just V1 pi, V2 pi, but the policy sounds like the same policy.
Yeah, this is all for the same policy, right? So there's no I policy here, right?
But on top, it sounds like different versions. You're trying to compare which one that's closely.
Right, so this I is over all K.
Yeah.
So K, I think if it's still dealing with the same variables, let's see. Oh, there's no more. In the other post, the K was the set of actions. I don't know whether it's the set of actions here or it's the time steps. I'm thinking it's
This
actions.
is more of trajectory here.
Trajectories here.
Certain rollouts or certain samples.
Okay.
Bunch of, yeah. But across all of them, I want to maximize the difference between these two value functions in this case.
Uh-huh.
One of them is the optimal value, which is the source. Another one is we do not know. We start with random and try to somehow adjust towards the. Okay.
So those of you who are online, do you have any insight that you'd like to provide? I think we should be able to hear you. Yeah. You want to unmute and discuss? Okay, so we'll try to go on from there. So this is the paper that we were just covering in the other blog post. So yeah, this is the maximum entropy one, where we're saying that there's a expectation, right? So the main assumption is the reward function is yeah, is something that can be calculated through parameters, and that's a function of the state, right? The reward is a function of the state. And then the value of a policy is this, you know, I've gotten a policy, right, that's given to me, and then I want to calculate the expectation of the reward over all the time steps, right, where I have the discounting factor, gamma to the power t for each of the time steps over that, right? And I'm just going to substitute in this perhaps learned network that is going to learn the reward function. I'm going to put it here. And then I can factor out the weights out of the expectation, right? So then I can use the feature expectation in this form. Right, so I have a number of features for this to generate the model. Any questions? Please help discuss, because I'm, again, yeah, this is the first time I'm seeing this too. Okay, so we'll go on to the next one. So in other words, the value is the linear combination of features expectations, right? Given an expert's demonstration, we want to optimize the reward function so that the resulting feature expectation matches as much as possible the expert's features visitation, right? So we want to find some optimal policy that we've estimated tilde pi, such that the difference between the expectation and the optimal policy under L2 is less than some epsilon, some capital epsilon. Then the value difference becomes something like this, where we decompose it into different parts, right? How do we interpret this? Oh, this is, yeah, just for the the value difference, right? This is the expected on the policy, and this is the one for the optimal policy.
This is the amount of discounted rewards somewhere. So left one is the difference.
Right, there's a difference here.
E is the expert. Pi E is the expert's policy.
Pi E is the experts.
Given the expert's policy, and on the right side, given is our policy.
This is our current policy. Yeah, current optimal policy.
And so the expectation or the discounted rewards we get across all the states, that particular trajectory or.
Right.
Yeah, and if you look at the difference between these two, both of them behave same, which means we achieve
exactly the right policy. The optimal policy and our estimated one are no different.
So there's a.
So he transposes it here, right? So we've moved this term over onto the left-hand side and this one over to the right-hand side here. How did we do that?
WT was always there in this case.
You mean up on this line?
Yeah. This line W.
Well, the WT comes from this part here, right? Because we're taking the reward function, and then we're modeling it through some type of network, right? Some type of supervised classification algorithm, maybe a neural net, right? So we're learning the weights over the basis functions, how to approximate the reward function given the state, right? So our WTs are there. So we're just exchanging the R that we have here for the model, right? The model is this WT times this mu T. Where's what's mu T?
Find the policy, first instruction, find the policy by some tilde such that the difference between is less than our threshold that we are interested in.
Right.
And that threshold is primarily based on the reward functions. The reward function internally, and then the rewards that we get in two different policies: the expert policy and then the policy, current policy that we are interested in. So you just somehow quantify that the expectation of the rewards as mu of the pi tilde or mu of E, the expert's mu, and then the current policies, the expectation, let's say. And then the want rate, so there's WT 2 times, just take it out.
Are you guys asking like what is it equivalent to the WT?
Yeah.
I think the WT is so I don't think they are actually like deriving it, but they're just using feature mapping. So like I think the mu here is the feature function.
Okay.
So
the basis functions
of a policy. Well, and then the WT, which will be equivalent to what we learned previously, was like all the weights for each feature, right?
Right.
And so I think that like the first line and second line is the equation.
Okay.
Then they are from there they are changing the right side of the equation to be an inequality.
Right.
I think that's what it's doing.
Yeah. But I'm just trying to understand why they swapped here. Because you can see here, this is the expert's policy. Now it became on this side.
Right.
But I think it doesn't matter because these are absolute values, right? So I guess it doesn't matter. You have a negative here, then you'll change to a positive. So maybe it's not.
That's absolute, right? That's not L1.
No, this isn't L1. This isn't L1. Yeah, that's very confusing if it was L1, right? So the L2 is over here, right? You have these double lines and then L2. So that's definitely the case up here. And also down here, but I think in these two cases, these are just absolute value, right? Yeah, math has this annoying property that
the same trap once before. And
correct. Yeah, it's not. So this I think is absolute value. So it's just saying that the absolute value, some positive quantity is going to be the same whether you reverse or not, right? And then because this is more convenient to get to this point here, right? Yeah. So you have the L2 of the weights, which you can then do what is it decay weight decay on as a constraint, and then the basis, the feature matching, right, for that part. So I guess that's what it's saying here, is that the concept of feature matching expectation, which is right here, would be really important. Occasionally we need the battery, otherwise it's going to die. I'll catch it on the other end. So I think we already covered this, but never hurts to do it again, right? So the key point here, I think, is that they've identified one big part of the bottleneck, right? Which is that you need to use standard RL, pretty much everything we've already talked about in this course, in order for us to compute the policy of an estimated reward, right? So you have this reward estimate, but in order for you to generate trajectories, you have to have a policy. It means you have to go do the forward pass of reinforcement learning before you can do the backward pass of inverse reinforcement learning. Right? So then step 6, rinse and repeat. Do this as many times as you need to until you get a reward function that looks like will generate the demonstrations that you saw. We didn't go through this one. This was also highlighted in the lecture. But I think maybe we should finish the GAN part first, and then if there's time and interest, we can go through the rest of the slides here. It's more fun to do it together. But yeah, it's right here.
I'm also not very sure about that. Let's try.
From here, right? You're coming from this slide onwards.
Yeah.
You can go to presentation.
Okay. So this slide straight away goes into some of the later derivations that he actually wrote. We don't really know about this WI, WG's role and stuff like that. Probably we skip this first, and then we'll go back to the GANs part and we'll revisit this idea. So let's just look at the plain old GANs. So I'm not sure how many of you guys are familiar with GANs here. Like some of you guys.
Anyone familiar with GANs? One, two, 2.5. Okay, looks like we need a review.
Okay, so yeah, so GANs it comes under generative model. Okay, it doesn't try to explicitly estimate the density function straight away. There are a few other methods. Variational autoencoders can do similar things as like what GANs do. In general, in GANs, we have two sections. One is the generator, and the other one is the discriminator. Probably I need another link. Maybe I can just...
Yeah, sure. Good search.
Let's look at some codes. We try to understand the GANs from code straight away. Nice presentation, yeah. So the idea here, right? So we have a generator which is a neural network. We have some weights associated with the network, And discriminator is also, you can think of this as one network or two different networks. They have different weights and different loss functions, but the generator is somehow linked to discriminator. Okay, but discriminator has no links to the generator in some sense. Okay, we will see that in a while. So we have some real data, and then maybe there's a data set, and we sample a bunch, maybe a batch from the data set. Maybe in this case, one or a batch it could be. And then here for the generator, we specify some latent vector. It can be a noise in this case, and in the initial version of the GAN, we just throw in some noise. The dimension of the noise is fixed. So if you look at if you learn a little bit about autoencoders, there is this concept of encoding and decoding part. You take an image, let's say a 100-dimensional image, and then you compress it to a 10-dimensional version of that, okay, through some encoder, and you call the 10-dimensional version as a latent vector. So given that latent vector, maybe the latent vector have like 10 variables inside, and you change one variable, that should be able to change some crucial part about the image. Maybe a person is smiling there, and if you want to tilt his face, or if you want to control this, how much you want to smile and stuff like that, maybe the latent variable should be able to do that. And this is the decoded part of a normal autoencoder. This portion here. Okay. So we throw in some noise here, and this noise we want it to generate. This is a neural network that should be able to generate an image that looks something like the original image. Okay, and then we want the discriminator should be able to predict. It's like a binary classifier here. We want to say whether the image is a real or a fake image. So if you think about loss functions for these two, discriminator and generator, okay, so when it comes to the inverse reinforcement learning with GANs, the loss function is the only thing that plays a crucial role. If you look at the slides. So let's try to understand the loss functions here. Okay, so if you think about the discriminator, given an image, we know that let's say in this case 8 is an image, and if you feed it to this discriminator, we wanted the image to be real, so it needs to be predicted as 1. So anything that's sampled from the real data, you want the output to be 1, correct? And anything that spitted out from the generator, you want it to be fake. So you just push all the values to 0, and anything that's come from the real distribution, it should be 1. Okay? So very simple loss function. So if you look at it here, especially the loss function. Okay? So this is the discriminator loss. Okay. So for the discriminator loss, for all the real values, we want to minimize it with TF.1s. Right? TF.1s like the logits from the real image. For example, you take a real image, feed it through the So for a real image, we want the outputs to be 1, and for the fake image, we want the outputs to be 0. Right? The 1 is sort of like smoothened here. So if you, I'm not sure whether you can see, there's a factor to smoothen the discrete step rather than strictly be 1. You can just put it 0.9. So that's the smooth and a little smooth concept to ease the training, I guess. And this is one loss for the real images. For the fake images, we want it to be close to 0. And look at this is actually from the D-logits fake. Ideally, this is coming from the discriminator. The generator. You take a random noise, you pass it to a generator. Generator spits out something, and this is the actual image from the generator. Okay, we want it to be 0, so that's why 0 light. So you sum that up. That's a loss function for your discriminator. Okay, and when you look at the generator, this is interesting because when you look at the generator loss, it's still the fake image that the generator generated, but we want it to be 1. We wanted to adjust our generator in such a way that the next image that it produced is closer in order to fool the discriminator. Okay, so the idea here is the generator will get initially the generator will be totally random. Have no idea how to fake this discriminator. Initially, the discriminator is so good in terms of classifying your original real data, and over time we want an equilibrium whereby the discriminator is somehow fooled by the generator, and generator is so good in terms of generating the real fake images. That's what we are interested in. Okay, this by itself, if we think about it from the slides perspective, let's go back to. I'm not sure where is that. Okay, here. Okay, so if you think about it from the slides perspective, we got a generator. A generator's job is to given a latent vector z, it can be a noise, and it has to spit out given z, it has to generate an x, or in this case we are modeling a distribution. Okay, given z, we have to generate x, and then with this generator we just sample a bunch of images given a bunch of noise. So we have a small data set. Okay, and then on the demonstration part we have original actual data, and from those images we just don't know who actually generated these images and how they generated. We only have access to the if you think about it, states and actions. Those are the only things that we have access to it. We just don't know how they decided to choose those actions and what is the sequence behind it, what is the goal, and we may not know. But given these two data sets, one is the actual data set and one is the fake data set that we generated, okay, from the generator. We want a loss function. So we look at this loss function here, which is okay. So there is two. Okay, this is the discriminator. Okay, there is a discriminator. We want the discriminators to say one, for example, for the data which is x coming from p star, which is our source of truth, or from the expert policy or whatever you can think of. And we also want if any data that comes from p theta, which is our policy, which is the generator in this case, it initially is fake or random. We want that to be as low as possible. Like we want the experts to be as high as possible, and the generated fake stuff to be as low as possible. That's why we have 1 minus that data, okay, that fed into the discriminator. Notice that the x is actually pulled from two different sources. Here the x is from p star. Here the x is from p theta. That's the difference. And then this loss function helps you to maximize this from generator. Sorry, this from the expert, and minimize from the generator. So some people call this min max. If you think about it that way. In this case, both we are trying to maximize both, because there is 1 minus this component, which is a minimized equivalent I can think of. Okay. And then, so that is the discriminator's side. How about generator? Generator, if you look at theta, which is the generator is parameterized by theta. So we want to maximize based. Sorry. Probability.
X sample from your.
Yeah, X sample from the generated fake images.
Yeah.
And this we want to maximize this.
There's a lot for real, like the definition for D is on the right side.
Which is here. Yeah. Okay. We want to maximize that this the X that is generated from the generator to we want this probability to be maximum in order to maximize in order to match the original source distribution. Yes. So we adjust our weights in the generator network so that it will generate the next source that should be as close as possible to the distribution of the demonstration site. Okay. Okay. So let's keep going. Let's see. Any questions on this slide? Also, no.
So I'll interrupt for a second and go to the research side. Find out this one. Screen here. So this is the paper that was mentioned on Slack. This is actually his paper, sorry, Levine's paper, that makes this connection between GANs and IRL. We go down on page 2, he explains this correctly, right? Normally, the generator takes noise as input and outputs a sample, right? Or the discriminator takes as input a sample X, right? And then outputs the probability dx that the sample was from the data distribution, real distribution, right? So the discriminator's loss, right, which is what we were just going over, which is then the average log probability assigned to the correct classification, which part, right? Evaluate an equal mixture of real samples and outputs from the generator. So both parts of this equation.
Yeah. So here, so this part.
Yeah, you can switch back.
Okay. Okay.
Yeah. So yeah, then it just says, okay, we're going to define the generator's loss as the sum of two variants, right? The two variants are here, right? So you can say the generator's loss is the opposite of the discriminator's loss, but instead of doing exactly that, we use the log of the discriminator's confusion instead. Right, so we're looking at a difference between the variables here. And
yeah, the only difference is the access from different source.
Yeah. Okay. So yeah, you can go ahead.
Okay. So okay. So, okay. So with this setting, and then you should be able to generate real fake images given these inputs, like given a bunch of celebrity. There are a lot of GANs out there. Damn lot of GANs. There are maybe I can share some GitHub at the very end. There's a consolidated GitHub repos. Let's see. Okay. Okay, so here, so here we are discussing more on the discriminator aspect and its loss function. So here, right, given X, what is the probability that it is being real? And that's the definition of the discriminator. And so if, let's say, what could be a best discriminator that we can think of is actually the ratio between these two quantities. One is the P star is the real distribution, the experts distribution, for example, and P theta is the one that we started with, which is our generator. Can be random initially, and over time it copies the actual discriminator. Actual source. So here, if, for example, given an image, and that image, if you look at the probability of that image being in the true set, okay, then this probability will be higher, and in the fake set, this probability will be lower, and then higher quantity divided by higher quantity will be 1, and that's best choice in that case. On the other hand, if, for example, a fake image, if you look at the probability of that fake image being in this source, may be very low, and a low quantity divided by a high quantity plus a low quantity, so low divided by high value, which is close to 0, right? And so this could be an ideal discriminator setting. Are we okay with that? We got that idea here? And then he expanded this p star of x and p theta of x. So for p theta of x, so there is the current policy p theta of the trajectory, which is directly proportional to the policy of the trajectory, and then exponential reward, okay, along the trajectory, and okay, that, and then choosing this. Okay, so let's see this. Let's see. I'm not very sure about this, but if someone wants to help out. So my understanding, I'm not very sure about this derivation, but the idea here is, here we are trying to modify the default discriminators definition. The original GAN's idea, if you do it, he's saying that you may not be able to capture the okay. So with GANs, you got generator and then the discriminator. So over time, generator should be able to capture the actual distribution that we don't know. It will try to match towards that, and then so here is saying that here is to capture the actual reward function. This adjustment is to capture the reward function instead of not only capturing the policy of that. Of that original the true distribution. So I'm not quite sure about this. This is it.
Okay, we can try from the original paper. Shall we do that?
Yeah. Where is it?
Okay, so I'll go back to screen share again. Hold on.
It's at 3.1.
Yeah, okay, great. So there's a part where in the original paper that we were just looking at, we want to show that GANs are basically can be applied to inverse reinforcement learning fine. So I think, yeah, so in 3.1, I didn't look at this part yet, but I think in the earlier part of the lecture, which I completely glossed over because I didn't really go through it, Sergey was talking about the maximum entropy version of the inverse reinforcement problem having a particular problem with calculating the partition function. So why do you need the partition function is because you need to normalize for all the possible trajectories that can be generated or policies that can be generated. So what he wants to do is then show that we can make this connection and then fold the problem of computing the fold the problem of creating the partition function into the GAN training procedure, right? So it says in this section here, we show that GANs, when applied to inverse reinforcement problems, optimize the same objective as maximum entropy, inverse reinforcement learning, And in fact, the variant of GANs, as described in the previous section, is precisely equivalent to guided cost learning. So guided cost learning in the lecture was covered a little bit. So I hope we can all go through this. Again, I can't say this specifically, but basically you have, again, the discriminator's loss, right? Which here is the expectation of the samples, the trajectories coming from the
theta.
this is the learned. Yeah, these are the learned things that are generated from the generator, right?
Mhm.
And then these are the ones that are the demonstrations, right? Is that correct?
What is the difference?
Well, basically we have these two parts, right?
Yes.
One is from the
From the original source, another one is from the generator.
right. So the generator one, let's see. Actually, yeah, I think this is the generated one, and these are the samples. These are the samples sampled from the gold data set.
Two different.
Is it the other way around?
Yeah. So the right one is the one that's
These are the samples that are generated,
generated.
and
The
these are the
real-
ones from the real
trajectories.
Yeah.
trajectories.
And then the B is set to be essentially the probability of the real trajectory over the probability of the probability of a trajectory that's. So I think B is just a likelihood.
Yeah, likelihood of saying given X, what is the chance of being real or fake?
Yeah.
Just it doesn't tell what is the source should be coming from.
It doesn't
Yeah,
care,
it doesn't-
right?
it
It's
doesn't-
just saying that there's a
Yeah.
sum
Yeah.
between these two parts.
And then the only thing here is P and Q, right? P can be one distribution, Q can be another distribution.
P and Q.
Yeah.
Uh,
Tau,
P.
P, tau from P
Yeah,
and
P
tau
is the
from Q.
real. I think it's the real. The real center.
Okay.
trajectory.
Yeah,
Q
let's,
is the
let's
generator.
go double check that, right?
P of tau is the
Right, P
actual
is the actual
distribution.
distribution of the
Yeah.
data. So these are the golden samples, right? And
Yeah.
these are the fake ones.
Mm.
Okay. So then this is right. This is the fake distribution,
Yes.
right? And this is the real one,
Our distribution.
correct?
Yes. And with that trajectory, we are expanding it out.
So what he's trying to say is that in the previous work on the maximum entropy inverse reinforcement learning, we have a very similar log likelihood objective, right? Which is the cost function here, which is equivalent to this bottom statement. Has an exponential loss function, again, between the actual samples, right, and then the generated samples, right? Q is the generated version, right? So where we have substituted the current best policy that generates a trajectory with this, right? We're using the current model to generate the importance weights.
Is this something to do with the importance sampling?
Yeah, so basically in the earlier part of the lecture, the one that we skipped over when I went to the blog post, he was saying that one way that you can deal with the maximum entropy approach to inverse reinforcement learning is to do importance sampling, right? Because when you fall off the trajectory, you have some problems using whatever is left, right? So we want to be able to use those weighted in an appropriate manner to help establish which way to go for the generator and the discriminator, right? Can I say that? So, right, we want to establish the following facts, which he does later. I don't think we're going to go over that. But the value of z that's being calculated here is equivalent to the importance sampling estimation for the partition function in the standard importance sampling maximum entropy IRL approach, right? So he's basically saying that using the GAN framework, you can do the same thing as what the inverse reinforcement learning is under the maximum entropy approach, right? For this value of whatever z, the partition function that's calculated, the derivative of the discriminator's loss with respect to the parameters theta are equal to the derivative of the maximum entropy objective function. So yeah, that means it appropriately fits. The generator's loss is exactly equal to the cos c theta minus the entropy of Tt. That is the maximum entropy policy loss defined in equation 2. Okay. Yeah, I don't think it's going to get too detailed from here, so I'm not going to go further with that. Shall we go back to your slides?
Yeah. So with that, we end up with this value for the d parameter, the discriminator parameters by tau for a particular trajectory. And so if we make this change, and this is the loss function, final loss function of the discriminator, what you're saying is with this change, we should be able to capture the reward function and also the policy that the generator is trying to fake. So let's see. And he also mentioned that we do not need importance.
This was the part that I was just making right now, that Sergey said basically that the GAN architecture doesn't have this problem of calculating partition function. Right? It's already absorbed into the way that the model is handling this.
So yeah, that's from the same as like previously. So now if you look at this, the pause, okay. And so here is we're showing the loss function for the generator. The generator needs to maximize the chance of that generated data and the trajectory that falls under the original. Falls under the expert distribution. So we need to adjust the theta, the generator's policy, which is parameterized by theta, with this loss. So J. Do anybody have any intuition about this loss?
Policy.
Yeah.
Right.
I was curious, how does this relate to the P star of tau? There is no intuition. Okay, the one thing is R pi is the one relation that we can think of right now. The reward.
You want to elaborate? Try.
I'll try.
Yeah, no worries.
So we're trying to find a good reward function parameterized by
Tau.
by the side. So
The one here, yeah.
we know that the expert demonstration should be able to reach a good amount of reward. So then what we were discussing previously, those slides, was how to match your reward function to the demonstration. But now with the reward function, we're training a new policy, and this policy should also be able to achieve good rewards using this generated, using the reward function that you derive from the demonstration.
The estimate of the reward function. Hmm. Yeah. In some sense, we want to maximize the um, the so there is an estimate of the reward function that we are trying to derive, right? There is a okay. So the data demonstration. There's a sample trajectory, a bunch of good optimal policy trajectory. State action pairs, but not rewards is shown. Only state action, state action, state action. The rewards are not shown to us. And from those good trajectories, optimal trajectories, there is a reward function associated with that, and that's why the good so we are trying to have an estimate of the reward function, okay, starting from a totally random policy that the generator generates, which we are not only trying to trying to adjust the policy from the generator to match against the policy from the original source. At the same time, we are estimating the actual reward function that is associated with the data demonstrations. I'm not very sure where is that estimate of the reward function is hidden. Is either this side or this side. I'm not very sure about it. If you guys have any intuition.
Which part again?
So from these data demonstrations, we have a bunch of trajectories, and these are actually the optimal policy, for example. And the rewards are not shown to us, but there is a state action pairs, a bunch of state action pairs. So with these actual optimal trajectories, okay, we want to learn, or we want to have an estimate of the actual reward function, which was not shown to us. Correct?
Yeah, that's the general IRL problem, right? Is to generate the reward function,
generate
right?
Or estimate, yeah,
from trajectories or policy.
Yeah, and we are controlling theta to have better and better policies, so that this the discriminator will not be able to identify whether this policy is actually coming from the fig generator or is it actually the policy that that is from the expert. If the generation process gets better and better of generating trajectory that is actually close to the expert's policy of rolling out this trajectory, okay, which also means that we somehow got the underlying reward function, right? If we can match this distribution from our generator somehow, we have an estimate of the underlying reward function, right? If that is true, okay. And this R tau for trajectory, this R tau, so this is like we want to maximize this reward parameterized by yeah, I got that. So this is actually the reward function R psi, right? R psi is the reward function, and that is parameterized by psi, and this is our current estimate of that. So we want to maximize this estimate. Now we got the idea, roughly.
Yeah, the connection is the psi, right?
Yeah,
so
psi.
The R psi, the R is generated
is the
because
function.
Of psi, which
yeah.
is the current best estimate of
the underlying reward function.
Yeah, what the reward function.
So that's the connection between. So here we try to minimize or almost want to kill this policy, and here we are trying to maximize the reward function that we have next. That the estimate of the reward function that we have here, the psi, okay, and when over time they find a perfect equilibrium that literally copies the policy and the underlying reward function, okay. Okay, so but anybody have any idea in this whole inverse RL, why do you need to have that reward function that you want to know? Like, why do you think that you need to have, you need to know about the reward function?
So that's part of the reason, but another part is because the reward function is more portable than the policy, right? So I think in this part of the lecture he hints that if you only recover the policy, and when there's a new constraint, then you won't be able to optimize for it. So for example, if you know that you're trying to get to a particular objective, the reward for it, you change the parameters of the problem, and you can adapt accordingly. So I guess in this set of slides, so you want to talk about that?
So this is exactly same as what we are discussing right now. So we want to decouple the goal from the dynamics. And so in some sense, policy is actually a combination of a reward and then the dynamics. So there was a demonstration with...
I don't think it's embedded in your slides, are they?
Yes.
Do you just want to play that part of the lecture?
Maybe.
It's up to you. Right? We can play it if you like.
Yeah.
So, maybe go to the screen. I will share again. So this is the first time I'm playing a video through a shared Google Hangouts to another screen. So that's sort of fun. Let's see.
Let's hope the bandwidth doesn't die.
Yeah, the battery is over here, so I hope it'll be fine. Okay. You can click that. Okay, so I gotta play it without that. So the thing. Okay, wait. That's why I'm on 2 times speed, because I was watching it while we were going through. Sorry about that. So the idea is that you have an ant that's trying to learn a behavior, like going to the right, and it's used all 4 limbs. But the problem is in the one on the right-hand side, they've actually disabled the 2 red limbs, so it can't function properly. So if you learn a policy, you'd be stuck because your policy only knows how to operate all 4 legs. Right, but if you know the reward function and say the whole point is to go to the right, then you can relearn a policy to do that, right? So now you have your limbs are stuck, you cannot operate them, but you know the reward, so you can just use normal reinforcement learning to learn the reward, right? So that's the portability of learning the reward compared to recovering the policy, right? So it has more generalization because you know the goal that the person is trying to achieve. So if you're not able to exactly clone the behavior, you can still reach your goal.
And also mention that once we have the reward function, we can always apply our normal RL techniques to be able to learn a policy on top of that. So the reward function is more important than learning a policy if you want to generalize better. So, okay.
I didn't die. I was surprised.
So what? Okay, so this is where if we throw away the discriminator definition just now we talked about, what happens if we use the traditional binary classifier being the discriminator? So it can able to copy the policy, but not the reward function. That's okay. It can generalize, cannot be optimized to the reward. Yeah, it's about the same. Yes.
So this part is just saying that instead of learning the reward function, I just copy the behavior, right? So that's imitation learning from lecture 1. Right? So the whole point of this part of this part was that said, okay, I just want to copy the behavior, right? So that's why it says down at the bottom left, right? Imitation learning. I clone the behavior. So the whole point is that when the discriminator runs, it should, at optimal condition, it shouldn't be able to figure out anything, right? It should be maximum entropy. It doesn't know how to distinguish the actual behavior that was sampled versus the actual, the generated policy. Okay, but then you don't have a reward function that's backing this, so it doesn't transfer, right? So if you have A robot that needs to do the same task and it's in the same controlled environment, probably imitation learning is fine, right? But let's say you stick a person in the middle of the background or something happens stochastically to the state, and then this is probably no good, right? Because you cannot trust imitation learning to get it done, right?
Yeah, thanks. So here we are just comparing with GANs with IRL and traditional GANs. So the discriminator being a classifier, but here the discriminator is actually the reward function, our estimate of the reward function. And this reward function we want for any random policy, the thing that the generator spits out, we want to minimize that. And at the same time, for those expert demonstration, we want those to be maximized. Because if you think about it, right, these two policies are like a bunch of trajectories from these have no they're not telling what is the reward function look like, and we have no idea about that. But the the discriminator is an estimate of the reward function. The only way we can tell is whatever the human expert did is actually good, and we want to push all those things to high reward, and we want the robot to, whatever that initially is random, we want it to be as low as possible. With this setting, when we start out, and then over time, what happens is all the things that robot did, the random policy that it spits out, all of it's going to be minimized. Like the rewards are going to be very, very low. So over time, this generator is literally copying the sequence of the human demonstration, which in a sense, since we already copied or have an estimate of the reward function from the human demonstration, and now the generator is getting better and better on spitting out trajectories that are more likely similar to the human demonstration, we will have an estimate of the underlying reward function. That's my view on this slide. You guys have anything to say? How many of you guys agree that this reward function is actually coming from the discriminator? Do you guys agree with that? If you remember this psi is the R of psi. If let's say R is the reward function, and we want to maximize, so this guy is the generator is trying to maximize directly, and here for all those things that the expert is doing, we want it to be maximum, and for all those things from pi theta, which is from the generator, we want it to be as minimum as possible, and this thing is the reward function. You got that idea? Yes.
This is different, right? This is saying that we want it to be maximally confusing to the discriminator, right? Where you can distinguish samples, actual samples from generated fake samples, right?
Yeah, but the reward function by itself, right? Where do we think we have that reward function here in this setting? Here, sorry. This reward function.
That's your psi, right?
Yeah, that's a psi. That could be a network parameterized by psi. Okay, then. But this assumes that we have the discriminator that follows this, which is derived previously. Okay, so
So you want to summarize?
So IRL infers unknown rewards from, or reward function from the expert demonstration. So that's the objective of inverse reinforcement learning. We want to infer the underlying reward function that the expert is generating its policies based on in order to maximize the future rewards that he will get. And the maximum entropy IRL is the first approach. You also talk about the forward and backward view, in which has some dynamic programming aspects to it. I'm not sure we talked about that.
We didn't cover that so much in the original paper, in the original part.
Yeah, while solving this. Yeah, this.
We should finish up soon, but I'll just say a couple words on that. So there was one part which we glossed over, which I'm trying to find. Right, which is that one of the key points that he makes about applying inverse reinforcement learning is that you can do it in the dynamic programming aspect for small state spaces and tabular environments, but to generalize it to continuous and large action spaces, it becomes a problem because of the need to calculate the partition function so that you can normalize the probabilities. So one of the parts that we've already also talked about is this problem where you have to run reinforcement learning every time, right? Because if you have a reward function estimate, you want your generator to create a trajectory, right? And to do that, you actually have to run reinforcement learning, right? So it becomes really, really expensive. Each time you have a new reward estimate, you have to go back, solve the reinforcement learning problem again. So what he hinted at is that this is one of the bottlenecks, the other one being the partition function. So what we want to do is the same thing as importance sampling in other places, is that spend the computation efficiently. So instead of learn the entire policy, what we're going to do is improve the policy at any time step, right? So we take an original policy, right? We have that already, and then we use this loss function in order to improve an existing policy from the previous round, rather than relearn the reinforcement learning problem from scratch, right? So that's what he calls lazy policy optimization, right? And so this comes again the problem that, as always, we have model representation problems. We could go off on the wrong tangent, and so we come back to this problem of importance sampling, right? So we've already dealt with that previously. So that's this guided cost learning, which I'm sorry, because I was asked to look at this problem at the last minute. I sort of glossed over when I went to the blog. Okay, but let's try to summarize everything that we covered today. Okay, so as we all know, right, inverse reinforcement learning says I want to learn the reward function given expert demonstrations. Right. We started with the very basic case where we had a tabular environment and we were actually given the policy. We upgraded that to a version where we still have the policy, but we go to continuous state space. And to solve the continuous state space problem, we had to, what did we do? I've forgotten now.
For the continuous space.
Right, we had basis representation. So we said the basis functions or feature representation is going to make it a linear programming problem. So we discretized it and make a very simple linear assumption for that, right? But then we said, okay, with that type of thing in place, we can get rid of the policy entirely, right? So we don't need a policy anymore. We use these basis parts. We can estimate the policy based on standard reinforcement learning, right? So we learn the policy given a current estimate of the reward function. So we just apply for reinforcement learning or standard reinforcement learning to get a policy, then roll out that policy to generate trajectories. And then we need to use a discriminator or something to help us optimize the system to generate better policies and better rewards, right? So it's an iterative cycle, right? We get better rewards when in the GAN, our GAN formulation, when the discriminator has a tougher time distinguishing synthetic trajectories that are coming from our current best estimate reward function compared to the actual sample gold standard demonstrations that come from watching the optimal behavior, right? Supposedly optimal behavior, right? And so we have both of these problems. So that's I think all that it says on this slide, right? That third algorithm is basically the sampling based method where we use for reinforcement learning to generate samples, right? And you can use it for a couple different things. Okay, the final part we covered was the adversarial imitation learning, which, like Bala said, it doesn't have this nice reward function estimate, which means it doesn't transfer to new environments where the states or the actions might change, right? So you can copy a behavior, but you won't transfer if there's differences. Okay. So that's it. Let's thank our presenters. So next week we have our exploration lecture. I hope those of you in week 11 are prepared. Again, it takes a lot of logistics to make sure people show up. It provides less value when people are not prepared, so I apologize for trying to do my best over the slides that I got to see. Okay, so yeah, hope you guys are getting prepared for your projects, and we'll see you next week. Thank you.
Thank you.
Right.